This is video number 4 on electric charges and fields. Timestamps are given in the description box. You can watch parts of video if you are running short of time. In this video, I'll talk about how to find electric field due to a continuous charge distribution. In particular, I'll find electric field due to a charge ring along its axis and also find electric field due to a charge disk at points along the axis. I'll discuss 3 conceptual questions. Finally, I will summarize this video. So instead of charge being concentrated at a point, as in the case of a point charge, it can be in form of a line or a surface or volume charge distribution. This is a line charge distribution. This is actually a curve, but this is a 1D distribution. This is a surface charge distribution, and here the charge is distributed in a volume. If you take a small element of this line charge, the charge of it will be lambda into delta L, where lambda is linear charge density. The units will be in coulombs per meter. So in this small surface element, its charge will be sigma into delta S, where sigma is surface charge density, and a volume element, its charge will be rho into delta V, where rho is volume charge density. It will be in coulomb per meter cube. The small element that we have considered is an infinitesimally small element that's very small. So it's as if it's a point charge. Electric field can be calculated using Coulomb's law, which is valid for a point charge. And since the element is infinitesimally small, it's like a point charge. So we can find electric field due to this volume element using Coulomb's law. So the electric field due to the volume element is K into its charge rho dV divided by the distance square into r prime cap. R prime is in the direction from the source charge to the point where we are measuring the electric field. So to find the electric field to this entire volume, we have to add electric field due to all the elements. We have to take element here, everywhere, and find electric field to the individual elements and add them up. So this adding of electric fields to the individual elements to get the net electric field is possible because of superposition principle. Using superposition principle, the electric field due to the entire charge distribution can be found by integrating. So this adding of electric fields is done by integrating. So the electric field to the entire volume element is volume integral of this elemental electric field, that is K into rho dV by distance square into r prime cap. Let's consider a specific example of a charge ring. The radius of the ring is capital R. We are finding electric field at points along its axis. So let us choose this point, which is at a distance x from the center of the ring, and let the edge of the ring make an angle theta at this point. To find electric field at this point, we have to find electric field due to an element. So let's take the element here. So electric field due to this element at this point will be in this direction, and the electric field is 1 by 4 pi epsilon naught dq by r square into r cap. This is by Coulomb's law. And definition of electric field: r cap is in the direction in the line joining the source charge and the point we are measuring the electric field, and we are away from the source charge. So this electric field will have two components. One is along the axis and one is vertically downwards. So if you take a diametrically opposite element, that is here, it will also produce an electric field at this point. The electric field will be in this direction. So this also can be split into two components, one along the axis and one vertically upwards. So the angle made by this electric field vector, this is also theta by symmetry because we are choosing the diametrically opposite element. So the vertical components will cancel each other and the cos theta component will add. Similarly, if I choose some other element here, there will be a corresponding diametrically opposite element here. So the electric field due to this pair will be along the axis, and the vertical component, one up and one down, will cancel each other. So any element, only the cos theta component will contribute, and the electric field is in the direction of the axis. So the electric field due to this element will be 1 by 4 pi naught dq by r square into cos theta, and it will be along the axis. To find electric field with the entire ring, we have to integrate this thing over the entire ring, and cos theta we can express in terms of xn capital R using in this triangle. So cos theta will be x divided by the adjacent side, that is square root of r square plus x square, and this r square is r square plus x square. So for different elements, everything is constant except for this dq. So if you integrate this thing to get the total electric field, it will become integral dq. Other things will come out of the integral sign because they are constants. And integral dq is the total charge of the ring, which is capital Q. So this is the expression for the electric field. So the electric field is 1 by 4 pi epsilon naught the charge q, and it should be 1 by distance square. And here 1 by distance square takes the form distance by distance cube. The distance in the numerator is the axial distance, this distance, and distance cube in the denominator is cube of the hypotenuse distance. So this hypotenuse is square root of r square plus x square. So cube of that is r square plus x square is about 3 by 2. That is the way to remember this formula. Let's consider some extreme cases when x is 0. So x is 0 means the point we are finding the electric field is at the center of the ring. So the electric field at the center will be 0 by symmetry. Electric field is force on unit positive charge. So a positive charge kept here will be pushed equally in all directions. So the net force experienced with the positive charge here will be 0. So that we should get from this expression. In this expression, if you put x equal to 0, numerator is 0, so the electric field is 0. Another extreme case is x is much greater than r. So we're finding electric field as point which are much farther away from this ring. So from a very far distance, the ring will appear as a point charge of charge q. So the electric field should come out to be 1 by 4 pi epsilon naught q divided by the distance square, that is x square. So in this thing, if you use that condition that x is much larger, so r square can be neglected. So the new denominator will become x cube. So x by x cube will become 1 by x square. So it's as if it's a point charge. So you could do a point charge when x is much larger than the size of the ring. Now let's find the electric field due to a charged circular disk along its axis. So this is a disk of uniform surface charge is sigma. The disk is very thin, and at the point where you're finding the electric field, we are at a distance x from the center of the disk. To find electric field, we'll take an elemental ring at, of radius r and thickness dr. And once you calculate the electric field of this element, if you integrate that electric field from r equal to 0 to r equal to capital R, the radius of the disk, we'll get the net electric field. Electric field due to this elemental ring, we can use the result we have just got, this one. So the electric field due to this elemental ring is K, which is 1 by 4 pi epsilon naught, into the charge of the ring, let it be dq, and 1 by distance square here takes the form distance by distance cube. The distance is the axial distance, this one, and distance cube is cube of this hypotenuse, this distance. So that is r square plus x square square root. So this is the electric field due to this elemental ring, and dq is 2 pi r dr into sigma. Sigma is the surface charge density, and the area of the elemental ring is 2 pi r dr. The thickness of this ring is dr. So if you integrate this thing for small r varying from 0 to capital R, we'll get the electric field with this entire disk. So the constant we can take out the integral sign, k, x, 2 pi, sigma are constants. We are not going to change from elemental ring to elemental ring. So the variables are r dr divided by r square plus x square raised to the power 3 by 2. This is a simple integration. We want to make a substitution r square plus x square to a new variable, say u, and r dr can be written in terms of du. So this becomes integral half du by u raised to the power 3 by 2. This is a simple integration, and we have to put the limits. So putting the limits, we get the expression as this one. and K is 1 by 4 pi epsilon naught. Using that, we get the expression for electric field as sigma by 2 epsilon naught into 1 minus x divided by square root of r squared plus x square. The way to remember this formula is electric field to an infinite sheet of charge of surface charge is sigma by 2 epsilon naught. But here the circular disk is of finite size, so the electric field is sigma by 2 epsilon naught into a factor, and this factor is 1 minus the axial distance x divided by hypotenuse distance. This hypotenuse of the outermost ring. This one, that is square root of r squared is x square. Now let's consider an extreme case where x is approximately 0. So we're getting close to the disk, very, very close. So as you get very, very close, from this point, it will appear as if the disk is infinite. So electric field at this point, which is very, very close to the disk, should be sigma by epsilon naught. So in this expression, if I put x approximately 0, then this second term will become 0. So the electric field is sigma by 2 epsilon naught. So when x is approximately 0, it's equal to an infinite sheet of charge, sigma. Let's consider this question. Find electric field to a charged circular arc at its center. You can pass and attempt this question. This is a circular arc, just got uniform linear charge density, and we have to find the electric field at the center of the circular arc. This circular arc is a part of a circle, so the center of the circle is the center of the circular arc. So to find electric field at this point, we'll take a small element here, and this is a symmetry line. The circular arc is symmetry about this line. Equal amount of arc is present on this side and on this side. It's in the middle. So theta is measured from this symmetry line in this direction. So let us take an element at an angle theta and of size d theta. So the electric field due to this element will be in this direction, and with this symmetry line, we will make an angle theta, vertically opposite angle. So we'll have two components, d cos theta and d sin theta. The electric field due to this element is given by Coulomb's law. This k, which is 1 by 4 pi epsilon naught into the charge of the element dq divided by the distance square. This distance is capital R, and dq is this charge q of the arc is distributed uniformly over an angle phi. Phi is the total angle of the arc. So it is q divided by phi into d theta. That is dq. And if you take a element on this side at an angle theta, which is symmetrically placed, the electric field due to this element will be in this direction, and will make the same angle theta. So this element will have a cos theta component along this direction and sin theta component along this direction. So the electric field due to this pair, this sin theta component will cancel. So only the cos theta component will contribute. So similarly, if we take another pair, cos theta component will contribute. So any element, only the cos theta component will contribute to the net electric field. So the cos theta component just multiply this by cos theta, and dE we have to use this one. So we'll get the integral as kq by pi r square to cos theta d theta. So k is constant, q is constant, phi is constant, r is constant. So the integral is integral cos theta d theta, and the integral of cos theta is sin theta. Putting the limits from the total angle is phi, so this angle is phi by 2. The direction of theta is clockwise, so this is minus phi by 2 and this is plus phi by 2. So the limits of integration are from minus phi by 2 to plus phi by 2. So putting the limits and simplifying, we get this expression. So the way to remember this expression is electric field to a point charge is kq by r square, and there is a factor 2 sine phi by 2 divided by phi. Now let's consider an extreme case where phi is approximately 0, not 0 but approximately 0, so it's very, very small. In that case, it's as if the charge of the full arc is located at this point. So it becomes a point charge. So the electric field due to this, in that particular case, where phi is approximately 0 is uh, like a point charge kq by r square. So if you use that condition that phi is very, very small, then sine phi by 2 is phi by 2. For small angles, sine theta is equal to theta, where theta is in radians. So phi by 2 is in radians. So sine phi by 2 we can write as phi by 2, and then simplifying we get kq by r square. So this is equivalent to a point charge when phi is approximately 0. This is the next question. Find electric field due to a charge line segment at a distance r from it. So this is a linear charge of finite size, capital L, and we are taking a point at a distance r from this line segment. This angle is 90 degrees, and this point P is located such that the ends make an angle theta 1 and theta 2. You can pause and attempt this question. Here is the solution. So let the x-axis be towards right and y-axis vertically up, and the origin is here. Let's take a small element of length dx, and the electric field due to this element will be in this direction along the line joining the source charge and the point where you're finding the electric field, and will be away from the source charge because it's positive. And let this element make an angle theta with this vertical, and the direction of measurement of theta is shown here. So this angle is theta. So this angle is also theta. So vertically upwards component will be d cos theta, and along the x-axis will be d sin theta. So the electric field x component is d sin theta, and d is k, that is 1 by 4 pi epsilon naught into the elemental charge dq divided by the distance square. The distance is this distance, that is x square plus r square. So distance square is x square plus r square into sin theta, and dq is the total charge q is spread over L, so it's q by L into dx, that is dq. So here for different elements the x will change and theta will also change, and theta and x can be related in this triangle. Tan theta is x by r. So from that we get x equal to r tan theta. So we will get dx equal to r secant square theta d theta. We have to eliminate one of the variables, and it's convenient to get the variable as theta. So we'll eliminate x in terms of theta. X is r tan theta, so it will become r tan square theta plus r square, that is r square secant square theta, and dx is this one. So putting and simplifying, we'll get this one. Electric field to the elemental element in the x direction. So get the total electric field, you have to integrate this thing. This thing makes an angle theta 1, and this end makes an angle theta 2. And so the limits will be from minus theta 2 to plus theta 1. Measurement of direction of theta is in this direction. So everything is constant, only except for the sin theta d theta. So it is integral of sin theta, that's minus cos theta, and putting the limits we get the expression as kq by Lr into cos theta 2 minus cos theta 1. This is in the x direction. Similarly, the electric field in the y direction is dE cos theta, and dE is this expression k dq, this one, into cos theta, and dq is q by L into dx. And again using the same substitution xn between x and theta, and simplifying we get this one. So to get the electric field due to the total line segment, we have to integrate this one from the limits minus theta 2 plus theta 1. So here will become integral of cos theta, which is sin theta, and putting the limits we'll get this expression. So kq by Lr into sin theta 1 plus sin theta 2. The way to remember this formula is electric field due to infinite line charges k into lambda by r, where k is 1 by 4 pi naught, and into 2. So here due to a finite line segments, k into lambda is q by L and 1 by r, and there is a factor because of the finiteness of the line segment, which is cos theta 2 minus cos theta 1. Similarly, electric field in the y direction It's k into lambda, which is q by L, and then 1 by r into this factor, sine theta 1 plus sine theta 2. So if we take a special case where theta 1 equal to theta 2, there is a point P is symmetrically placed. So if we are finding electric field at a middle point, so electric field is force on unit positive charge. So unit positive charge placed here will experience force equaling the positive x direction and negative x direction. So net electric field in the x direction should be 0, and there will be net repulsive force in the y direction. So if you put theta 1 equal to theta 2, the expression for electric field in the x direction is 0, because theta 1 equal to theta 2, but in y direction you will give an electric field. So when theta 1 equal to theta 2, electric field in the x direction is 0, unit positive charge will be equally pushed towards positive x direction and negative x direction. But in the y direction there will be a net electric field. This is the next question. Electric field to a charge ring along its axis is given as this expression we already got, which is 1 by 4 pi epsilon the charge q into distance, the axial distance divided by the distance q, which is cube of the hypotenuse distance. Axis of the ring coincides with the x-axis and center of the ring is at x equal to 0. How does the electric field, the x component, varies with x? Plot the electric field versus x. You can pause and attempt this question. So looking at this expression, when x is 0, the electric field is 0. And also when x is very, very large, the denominator r square can be neglected. So the denominator will become x cube. So it is x by x cube, it's 1 by x square. So when x is very, very large, the electric field will die out. So the electric field is 0 at x equal to 0 and also at infinity and also at minus infinity. So somewhere in between, the electric field should reach a maximum and then it should die out. So to find the maximum point, this is a standard way of getting the maximum point. You have to differentiate this thing with respect to x and then equate it to 0. So we can forget this constant 1 by 4 pi epsilon naught. Q is a constant. So the value variables are x divided by this thing raised to the power 3 by 2. So if you do the differentiation and put it equal to 0 and do simplification, we'll get the x for maximum electric field as r by root 2. And 1 by root is approximately 0.7. And to get the value of the maximum electric field at this point, you have to put x equal to this value in this expression. So if you put that and simplify, we get the value of maximum electric field as kq by r square into this factor 2 by 3 root 3. So this is electric field to be a point charge of charge q. So that into this factor is a maximum value of the electric field. So the plot of the electric field versus the distance x will look like this. At x equal to 0 it is 0, and at far off distance it dies down as 1 by x square. So it increases, reaches the maximum, and then it dies out. So the place where it reaches the maximum point is 0.7 r. To summarize, the electric field area volume charge distribution is given as volume integral of k into rho dV divided by r prime square into r prime cap. K is 1 by 4 pi epsilon naught. Electric field area ring of charge along its axis is 1 by 4 pi epsilon naught q into the axial distance divided by the cube of the hypotenuse distance. Electric field area charge circular disk of radius r along its axis is sigma by 2 epsilon naught into 1 minus the axial distance x divided by the hypotenuse distance square root of r square plus x square. For a line charge of finite length capital L and the electric field at a point P, which is at a distance r, and the ends make an angle theta 1 and theta 2. The electric field in the x direction is along the length of the line segment, and y direction is vertically upwards. So the electric field in the x direction is kq by L 1 by r into this factor cos theta minus cos theta 1, and electric field in the y direction is k lambda is q by L and then 1 by r into this factor sin theta 1 plus sin theta 2. I also take doubt solving sessions for physics and maths subjects of JEE and NEET. If you're interested, you can contact me. Fees is nominal and first class is free. Description box has got links and timestamps. You can watch WhatsApp video that you find interesting.